Hi, folks. We're continuing with Fourier series, kind of the second half of the video for Fourier series, continuing from the last one. And we had stopped when, after talking about some of the properties of the Fourier series coefficients, right? We said if x of t was even, then the Fourier series coefficients were even. If x of t was even and real, then they were real and even. If x of t was real and odd, then the coefficients were purely imaginary and odd. And we had looked at one thing that happens when you shift something in the time domain, a signal in the time domain. What happens in the frequency domain is that the coefficients get an additional phase term to them. So you have basically the same coefficients that you had before you did the shift, but the shift adds a phase term. So a time shift corresponds to a phase shift. In the time domain, you get a time shift. In the frequency domain, you get a phase shift. Now, this one, what I want to start talking about is what is the meaning of these coefficients? Because a lot of times what happens is we start looking at these coefficients as just numbers, and we say a1 is equal to 1 over pi, a2 is equal to 0, a3 is equal to minus 3 over pi, or whatever. And we forget that those coefficients actually tell us something about the size of the frequency component included in that waveform. So let's start with a very, very simple periodic function that you're all familiar with. And let's look at its Fourier series coefficients. So suppose I have x of t is equal to cosine of omega naught t. Right? So what are its Fourier series? I suppose we could go through all the integrals and all that kind of stuff to find out what the Fourier series coefficients are. But we already know how to represent cosine omega naught t in terms of complex exponentials. And this is equal to 1/2 e to the j omega naught t plus 1/2 e to the minus j omega naught t. So the Fourier series is of the form summation a sub n e to the n j n omega naught t. Let's compare this expression with this expression, and you can see that here what you have is n is equal to 1, and here n is equal to minus 1. So this coefficient here is actually the a sub 1 coefficient, and this coefficient here is the a sub minus 1 coefficient. And because cosine omega naught t is even, the coefficients are also even. So a sub 1 is equal to a sub minus 1. This 1/2 is not just a sub 1. This 1/2 tells you something about the power in this frequency component, right? You can't just think of A1 by itself. You have to think of A1 as the frequency component at frequency omega naught. Okay? We can do our other simple functions. So we can write x of t to be sine of omega naught t. And we know that this is 1/2 e to the j omega naught t, 1 over 2j e to the j omega naught t, minus 1 over 2j e to the minus j omega naught t. So again, this thing here is just n is equal to 1, so a1 is equal to 1 over 2j, and a sub minus 1 is equal to minus 1 over 2j. Okay, sine is odd, and therefore this Fourier series coefficients are odd. Sine is real and odd, so the Fourier series coefficients are purely imaginary. Okay. What happens if I give you something and I say, here are two signals. One has Fourier series coefficients like this, and another has Fourier series coefficients like this. And I give you two functions. One function is, say, going like this, and the other function is going, say, like this, right? And I say which coefficients belong to which function. You should be able to look at this and say, well, you know, this is a higher frequency, and these are both sinusoids. These are both some kind of sinusoids. So, but this is at a higher frequency, and this is at a lower frequency. Lower frequency means slow change, and this one is changing slower than this one. So these coefficients belong to this function of time, and these coefficients belong to this function of time, right? You should be able to look at this and this and understand what they represent, right? If I had, say, another one, and this had a coefficient here, and here, and here, the corresponding signal would look like this because it has the same frequency, but it has a DC value, so it would be something maybe like this, right? So the same frequency as this, because these are continuing on the other side, the same frequency as this, but because of this extra coefficient, this cosine gets raised. So don't think of the Fourier series coefficients as just these numbers, A1, A2, A3. That's very easy to fall into that trap. Think of them as actually representing a sinusoid. Okay. How would we extract these sinusoids from? You know, this is nice and simple. I can make it a little bit more complicated, I suppose. Let's suppose we have something a little bit messier. And let's suppose we have a set of coefficients, which are, say, this one, and another one which is, let's put it in the same place. So this is larger values, and this is smaller values. Okay, and I have two time functions, and one of them is, say, like this, and the other one is, it's say something like this. Is very poorly drawn, but the idea is this. Here I have a high frequency signal, two signals, a high frequency signal and a low frequency signal. The high frequency signal has a small amplitude, but the low frequency signal has a large amplitude, right? Here I have, again, a high frequency signal and a low frequency signal, but the high frequency signal has a large amplitude and the low frequency signal has a lower amplitude. So the low frequency signal having a lower amplitude would correspond to this. The high frequency signal, the low frequency signal having a lower amplitude would correspond to this. And the high frequency signal having a lower amplitude would correspond to this. Okay. So what we want to do is we want to take a look at how we would extract these different frequency components from a periodic signal. So it's given a periodic signal. Let's suppose I have a periodic signal. And if it's a periodic signal, I can represent that as a to the a sub n e to the j n omega naught t as a sum of exponentials. And what I want to do is take out certain frequency coefficients from here. Okay, let's suppose I want to take out the DC and the first component. What can I do? Well, I can put it through a filter. And how would I do the filtering? Well, that brings us back to where we started from. If you remember, for a linear time invariant system, we have this property that if I have e to the j omega t as an input to a linear time invariant system with an impulse response h of t, then the output will be e to the j omega t h of omega, where this omega and this omega are going to be the same. So if I say this is e to the j omega naught t, then this would be e to the j omega naught t, e to the j omega. Right? So let's suppose, and this is a very, very unreal filter. Let's suppose I have a filter. And by the way, sometimes people will write h of omega like this. Sometimes they'll put e to the j omega, because if you remember h of omega, the way we obtained it was we took minus infinity to infinity h of t e to the minus j omega t dt. So we can say that we integrated out t, and the only variable left is omega, which is what I prefer to do. But sometimes you will also see people saying, well, we integrated out t, so we're left with j omega, so this should be h of j omega. So I'm going to mostly write it like this, but if I slip and I write h of j omega, you know what I mean. Okay, so let's pick an h of j omega, which is really kind of weird, which is 1 when omega is less than, say, 1.5 omega naught, and 0 when omega is greater than 1.5 omega naught. Okay, and then what we'll do is we'll pass this signal through this filter with this, this is called the transfer function, by the way, with this transfer function, and we will get out the DC coefficient and the first frequency coefficient. And the reason we can do that is, remember that e to the j omega t, if I put it into this filter, I get e to the j omega naught t h of omega naught. If I put in e to the j omega, say 2 omega naught t here, into a filter, into a linear time invariant system acting as a filter, then the output I'll get is e to the j 2 omega naught t h of 2 omega naught. So if I put in a sum of these complex exponentials, so if I put in a sub n e to the j n omega naught t, I'll get out the output y of t will be equal to summation a sub n e to the j n omega naught t h of n omega naught. Right? So if the filter looks like this, then this one, so the filter looks, if I plot it in omega, it looks like it goes from 1.5 minus 1.5 to 1.5 omega naught. The coefficients here, a sub n, if I plot those in terms of their frequency, which frequency they're associated with, a1 is associated with omega naught, so it has some value. I'm just making it up here. So this is omega naught. A2 is, and this is minus omega naught, so this is minus a1. A2 is associated with the complex exponential e to the j 2 omega naught, so a2 will be somewhere over here. A3 is associated with the complex exponential e to the j 3 omega naught, so that will be, let's suppose it's negative, that will be over here, and a sub minus 3 will be over here, and so on. And of course a0 is associated with the DC value, and that will be over here. Now notice what happens when I pass this signal through this linear time invariant system. Each component gets multiplied, each component here gets multiplied by the transfer function evaluated at that frequency. So this one, a0, will get multiplied by the value of h of omega at 0. a1 will get multiplied by the value of the transfer function at omega naught. A2 will get multiplied by the value of the transfer function at 2 omega naught, and so on. And as you can see, everything outside of these three coefficients, a sub minus 1, a1, a0, and a1, everything else is being multiplied by 0. These three coefficients are being multiplied by 1, so we'll get in here, we'll get a sub minus 1 e to the minus j omega naught t plus a sub 0 plus a sub 1 e to the j omega naught t. Right? And I'll be able to, depending on what the values of a1 and a sub minus 1 are, I'll be able to write this as a0 plus, assuming that this is even, then this will become 2a1 cosine of omega naught t. Right? And if I plotted this, it would be, depending on the value of a0, if a0 is not 0, then this will be a raised cosine. If a0 is 0, then we'll just get something like this. And the period here of this cosine would be 2 pi over omega naught. Oops, I went. So the period, if a0 is 0, then we'll get something like this. And the period will be just this 2 pi over omega naught will be the period of this thing. Okay. What if we wanted some other coefficients? What if we wanted the second coefficient? Then what I could do is I could set h of omega to be equal to 1 for, say, omega greater than 1.5 omega naught. Let's make this a little bit, so 1.5 omega naught less than absolute value of omega less than, say, 2.5 omega naught, and 0 otherwise. And if you do that, then what you have is the filter then becomes, so here's my filter. Here's omega naught, 2 omega naught, 3 omega naught, and my filter goes from 1.5 omega naught to 2.5 omega naught, and on this side this is minus omega naught, minus 2 omega naught, minus 3 omega naught, and the filter goes like this. The coefficients, if you remember, are going to be here, 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 and so on. And when I multiply these things, the only coefficient that is being multiplied by something that's non-zero is the third coefficient. The second coefficient, right? So in this case, y of t will become a sub 2 e to the j 2 omega naught t plus a sub minus 2 e to the minus j 2 omega naught t. And if I combine these two, I'll get some kind of a cosine at 2 omega naught t. Right? And I'll get some value, and the value will depend on a2. Again, let's assume that this is an even function here so that I can write this as 2a2, right? And I don't have to worry about the phase. And if that happens, then it will correspond to some sinusoid whose height will be this coefficient, and whose frequency will now be 2 omega naught t. So if I looked at one period of this cosine, then this period would be 2 pi over 2 omega naught. Right? And you'll see some questions like this on the post quiz, where I've got a periodic function and I put it through a filter, and I'm asking you to identify which is the output of that particular filter. Okay. There is one other thing that I want you to know about the Fourier series, and that is that it doesn't matter if you look at something in the time domain or in the frequency domain. It doesn't matter if you look at x of t or the Fourier series representation of x of t. The object which it's being represented is exactly the same, right? So the power that is contained in the signal in the time domain is going to be exactly the same as the power in the frequency domain. And this idea that the power in the time domain and the power in the frequency domain are identical is called Parseval's identity. So if I evaluate the power in the time domain and I evaluate the power in the frequency domain, the two of them should be equal. Right? So how do you evaluate the power in the time domain? You take integral of the magnitude squared of the function that you're looking at. And then the frequency domain, the power is in the coefficients. So you take the sum of squares of the absolute values of the coefficients. And the Parseval's identity says the two of them are going to be identical. Okay, I think that's it. We'll leave Fourier series here. We'll come back to some of these concepts when we talk about Fourier transforms. The whole idea of time shift and phase shift and the evenness and oddness of functions, but we'll talk about magnitude and phase when we start talking about the Fourier transform.